Section 1.1, Real Numbers and Their Graphs. The three objectives for today are to look at graphing real numbers on a number line, comparing the values and characteristics of numbers, and finding the absolute value of numbers. First, we need to take a look at our number systems. In general, we have real numbers. Later in the year, we're going to talk about something called imaginary numbers, but for now, we're going to talk about real numbers. We start with the real number system. And within the real number system, we're going to see from this diagram that there are several subsystems. First, real numbers can be categorized into rational and irrational numbers. When you think about rational numbers, think about the word rational and what it means. If someone acts in a rational manner, they act in a manner that can be, say, predicted or in some sort of coherent manner that you would expect them to behave in. Whereas somebody acting irrationally would be somebody that you would consider, maybe use the term off the wall, or they might not be able to control their emotions. They're acting very irrationally. So keep that in the back of your mind when you're thinking about rational and irrational numbers. A good example for rational numbers are numbers that can be predicted, and here's what I mean. If we look at some examples, let's start with a simple fraction such as 4/5. And 4/5 will reduce to 0.8. Now, if we wanted to, we could continue and say 0.8000000 infinitely, and there's an infinite amount of zeros that go on. We could even go as far as to put a bar over it to show that zeros go on forever. But what you'll notice is that the decimals here can be predicted. You know that zeros go on forever. So that's one way of identifying a rational number, to look at the decimal and see that it has some sort of a value that can be predicted. Now, if I look at something like -2/3, though, at first it seems, all right, well, this is not an easy decimal to look at, but it also can be predicted because it's really 0.6 repeating. Well, it's negative because -2/3, but it's 0.6 repeating. So it's 0.66666 forever and ever. So those can be predicted. What you can also notice is that rational numbers can be expressed as fractions. And that's the easiest definition to remember for rational numbers. Okay, again, numbers that can be written as fractions or repeating or terminating decimals. And we'll go over definitions on the next slide. Irrational numbers are numbers where decimals go on forever with no pattern. For example, the square root of 2. If we look at the square root of 2, we have 1.4. 1, 4, 2, 1, 3, and it goes on forever, and there's never going to be a pattern here. That's what an irrational number is. If you look at this, there's no way to write this so that we could put a bar over the decimals. Another example would be something like pi. Pi is an irrational number. Its decimal places go on forever with no pattern. If you want to remember for irrational numbers, the easiest example is to think about any square roots of non-perfect squares. So for example, something like square root 9, well, that becomes 3, so that wouldn't work. But something like square root 10, 10 is not a perfect square. The square root of 10 is going to be 3 point, and then it's going to go on and on forever with no decimal repetition. All right, let's go back over here now. Let's take a look at our rational numbers. Within our rational number set, we're going to see the next set are called integers. And what integers really are simply whole number values and negative quantities. So for integers, we're looking at quantities like so. -3, -2, -1, 0, 1, 2, 3, and so forth and so on. So integers are all of our whole numbers and their opposites. Well, what are whole numbers? Whole numbers are simply 0, 1, 2, 3, so starting at 0. And then finally, we have natural numbers, which are similar to whole numbers, but we start with the number 1. Okay, those are our counting numbers there. So to define these terms, let's take a look. First, natural numbers, also called the counting numbers, as we said a minute ago, because when you count, you start with the number 1, 1, 2, 3, etc. Okay, so it's the counting numbers are where you begin counting objects. Whole numbers are similar to natural numbers, but with the inclusion of the number 0. Okay, easy way to think about that. Integers are really just the whole numbers and their opposites. So you have negative or positive values. Again, rational numbers are predictable. They can be written as a fraction or as a terminating or repeating decimal. And you could think of them as a ratio of two integers. Again, a ratio is the same way of thinking of it as a fraction. Irrational numbers have decimal places that go on infinitely without any pattern. That's the key. Okay, decimal places without any pattern. It is unpredictable. Now, let's take a look at number lines. This should be a refresher for you from your previous courses. But number lines we want to think about is that each point on the number line is paired with exactly one real number, and this is called a coordinate. And this is one of our most basic definitions of coordinates. So we're looking at a coordinate on the number line system, not on the Cartesian plane, not on an XY axis. So if you were asked to graph the coordinate -2, it's simply right here at -2. Okay, and we're going to do a lot more with number lines, and we're going to look at inequalities and solution sets, but this is the most basic interpretation of a number line. Okay, always think about number lines whenever you're thinking about adding and subtracting. It's an easy way of doing math. Let's take a look at the first example. Find the coordinate of the point 2/3 of the way from A to B on the number line below. So 2/3 of the way from A to the B. So the distance from A to B, what is it? Let's take a look. It looks like it's 6 units, right? From here to here. I see that I've got 4 units there and 2 units there. I'm looking at positive and negative in that sense. So it's 6 units long. Well, if I want a point that's 2/3 of the way, I want to say a point that is 2/3 of the distance, which is 6, of means times. So I want a point that is 4 units away. But 4 units away from where? This is not my answer. I want a point 2/3 of the way from A to B. So start at A and go 4 units away toward B. So I go 1 unit, 2 units, 3 units, 4 units over. This is my location that I'm looking for, which is the coordinate simply 2. Again, we're looking for a coordinate 2/3 of the way from point A to point B, which means start at point A and count over 2/3 of the way there, which happens to be 4 units. So our answer for this problem is the coordinate listed at 2. Alright, let's take a look at a second example here. On the number line shown below, determine the coordinates that are half as far from A as they are from B. Half as far from A as they are from B. Now, notice it says coordinate with a parentheses S there. Make sure you understand that what this means here is that there could be more than one coordinate that satisfies this condition. So what we're going to look at here is we're going to say to ourselves, well, we might want to use a little bit of algebra here. So what we're going to think about here is the fact that it says that the point is half as far from A as it is from B. So that means that if, say the point was 10 units away from B, it would be 5 units away from A. So it's always going to be closer to A, really. Okay, it's always going to be closer to A. So what that means really is that the point that we're looking for is either going to be to the left of A, somewhere in this region, or it's going to be somewhere in here, closer to A than it is to B. The point won't end up being here, because that's closer to B. We want it to be half as far from A as it is from B. So it's got to be somewhere in this region. And that's a good way of thinking about it already. So what we can do here is we could say the distance between A and B is 6. So by inspection, we could say that, well, you know what? If this is 6 units, we could say, well, this is 2 units, that's 4 units. And some of you might be able to notice this, that one of our answers is definitely going to be here. And let's make a proof of it. This distance is 2, or show proof. This is 4. So the distance away from A is 2, the distance away from B is 4. Thus, the coordinate is half as far from A as it is from B. So -3 is definitely one of our answers. But the question becomes the other answer. Where is it? It's definitely somewhere over here, but we can't just assume again and look by inspection. So now we want to use an algebraic approach. Here's what we can do. We can pick some dummy variable or some random location, it's called, and pick something over here, okay? Anything. So we'll just call it X. Now, we want the distance from A to be half of the distance from B. Well, how do you figure out the distance between whatever this X is and A on the number line? If I want the distance between these two right here, all I need to do is subtract them. So I really take the bigger number, which is A, and I have to subtract that from whatever the coordinate is, which we're calling X right now. Now, again, this is the distance from the random point that we're calling X right here to A. The distance between the random point and B is going to be whatever this coordinate is, which is B, minus X over there. So the distance from B to that point is really B minus X. And try it numerically. if you wanted the distance between any given points, or any two given points, you would say, if I wanted the distance between here and here, I would say, well, what is 1 minus negative 2? Well, 1 minus negative 2 is 3. And that happens to work out. There's 3 units apart. So what we're doing here is we're making definitions for our distances. But we were told a minute ago that the distance from A is half that of B. It's half of that of B. So if I took this distance here, and I compared it to this distance as a ratio, it should equal 1/2. It's half of the distance. So here's what I'm going to do. I'm going to say that A minus X over B minus X is really equal to 1/2. Now we know what A is and we know what B is. A is -5 and B is 1. So we can plug in and just solve for X. It's a bit interesting to look at this method, but it does work. And if we tried it with the earlier part, where we got -3 for our answer and we did it the same way, it would have also worked, and we can prove that in a moment afterward. Let's plug in. So again, A is -5, so that's going to go in here, and B is going to be 1. So we have -5 minus X over 1 minus X equals 1/2. Let's continue and move down. If at this point I want to think about this and cross multiply, I can. If I cross multiply, I'll cross multiply in this direction first. When I do that, I'm going to have to remember to put parentheses around here and distribute the 2 to both terms, yielding -10 minus 2x. When I cross multiply here, the 1 here has no effect, really. So that's just going to equal 1 minus x. I can add the 2x to both sides, and I can subtract the 1 to both sides, and I'll end up with getting -11 equals x. Again, I assume that everybody can solve this step here. So this indeed does show us that there's another point that's half the distance from A as it is from B. Well, let's check that to make sure. So let's just quickly draw a quick number line here. So we know that the answer was -11. So let's just put a mark here at -11. Well, A was at -5 and B was at +1. So well, what's this distance here? It looks to me like this distance is 6. And it looks to me like this distance here is 12. So indeed, this distance is half of this distance here. So -11 does work. Maybe I'll leave the extra part for you to work on if you'd like to, where you could use the same method but check to see that -3 also works. Now we're going to take a look at inequalities in number lines, and remember that an inequality is used primarily as a method of comparison. Okay, but there's many other applications that we're going to see here. So example 3. Graph the numbers -0.5 and 5 on our number line and write an inequality statement comparing them. So let's start with our number line here. I know that I only have to go as far back as maybe -1. There's 0, 1, 2, 3, 4, 5, there's 5. Alright, so graphing these, here's -1/2, and here is 5. And when I look at the two of these, if I wanted to write an inequality statement that compares the two, I need to remember and think, I have greater than and I have less than. So what can I write? I can say that 5 is greater than -0.5. How do I know that? Well, because take a look. 5 is over here. 5 is to the right of -0.5. So whenever anything is to the right of the other number, it is greater than that number. But -0.5 is to the left of 5. So you could also have written it this way. -0.5 is less than 5. So either of these answers are correct in this case. Very basic example of number lines and inequalities. Let's take a look at absolute value. So first, we need to remember that absolute value of any number is really the distance from 0 on the number line. So what this means really, okay, if you think about it, is that no matter what, we're going to be looking at a positive value because a distance is a positive amount. So for example, if I wanted to know the absolute value of -3, and many of you have seen this before, well, the answer is just 3, but let's talk about how this works. Here's -3, here's 0. Well, what is this distance here? The distance is just 3. It's 3 units. Whether it's going to the left or right doesn't matter because it's the distance. So that's a distance of 3 units. So what we can say to generalize, and if you think about this, it makes sense, we could say the following. The absolute value of A is always equal to, and we're going to have a piecewise answer. It's equal to A if A is positive. So if A is, say, 7, then the absolute value of 7 is still just 7. But if A is negative, for example, in this case, when we have a negative under the, or inside of the absolute value bars, the answer turns out to be positive. So this is equal to the opposite of A if A is negative. So whenever A is negative, again, whenever A is negative, the absolute value is the opposite of A. And that's what this is saying. Well, if A is 0, well, then the absolute value is just 0. So what we have is three conditions. Again, the absolute value of A can take on any of those possibilities if we know what A is, if A is positive or negative, etc. Let's take a look at example 4 here. In example 4, it says determine the value of the following expressions. Well, absolute value is just like parentheses. So if we remember PEMDAS, we have to do the absolute value parts first. So let's take a look at part A. Well, it's simply 3 times 6, because the absolute value of negative 6 is just 6, so this is just 18. So that's an easy example to start with. Let's take a look at B. In part B, we have absolute value of 4 minus absolute value of negative 7. Well, the absolute value of 4 is 4. The absolute value of negative 7 is just positive 7. 4 minus 7 is negative 3. So again, it is very important that we take a look at this and we do the absolute value first, because had you not, and had you done 4 minus negative 7, that turns out to be 11. Okay, so the order of operation is extremely important here. And finally, the last example here, well, we have to do what's inside the parentheses first. So in this problem here, we can't take the absolute value of anything because we have to do this operation first inside. So let's take a look at 3 minus 5 first. So what we have here for part C, again, is this. We keep the bars and do the math on the inside, which gives us negative 2, which is really just 2. Okay, again, absolute value also follows order of operations. Your homework for this section is the following: 1 through 39,